So I'm very pleased to be here. As Ivan said, I'll be talking about robust and energy efficient Mac and PHY strategies of Wi-Fi. I'm very pleased to be here. I heard about WINLAB for a long time. Actually, even when I was a graduate student in late 90s, and finally I'm here. And I was really surprised to see this Orbit testbed, and I hope that I can deliver some interesting talk today and we can interact together. So Wi-Fi, which is now part of our indispensable part of our daily lives, which Wi-Fi usage is growing more and more today. And as you can see in this graph, actually the Wi-Fi shipment has been growing tremendously. And if you take a look at this graph, we use Wi-Fi with our laptops and also smartphones, and more electronics which are not smartphones and computers are being equipped with Wi-Fi. And this year, 8 billion global Wi-Fi shipments are expected. So if you take a look at the evolution of Wi-Fi, actually, I don't know if you know, but Wi-Fi started actually late 90s, and it has been evolving. So starting from the original Wi-Fi 11B, AG, N, and now we are using 11AC. Well, actually, there has been a lot of development, but one of the things which evolution kind of happened was basically to support a higher speed Wi-Fi transmission. So to that end, basically what happened was more and more complicated and state-of-the-art physical layer technologies were developed and kind of defined as part of Wi-Fi. So for example, MIMO and also wider bandwidth were kind of defined. So 11AC standard defines up to 8 antennas usage, while the commercial devices support normally up to 3 antennas. And also if you talk about the bandwidth, up to 160 megahertz bandwidth is defined, while today's 11AC products normally support up to 80 megahertz. And also if you go to medium access control, one of the features which today's Wi-Fi include is frame aggregation. I'll talk about it more, but basically by aggregating multiple frames together and then transmitting those in a single packet, basically the MAC overhead, protocol overhead can be reduced so that the user perceived throughput can be enhanced. So that's good that we have all the good features in the physical layer and MAC layer, but the downside is as the transmission rate increases, the transmission might be less robust, so might involve more errors, and also they might be more energy hungry. So in this talk, I'll talk about how to handle this robustness and also how to make today's Wi-Fi more energy efficient. As I said, basically I'll talk about the robustness of Wi-Fi and also energy efficiency of Wi-Fi. So the rest of my talk will be divided into 2 parts. So let's talk about the robustness first. Especially now I'll talk about mobile environment. In old days, Wi-Fi was used mainly while you are sitting like this, right? But actually today, we are using Wi-Fi while we are moving around, especially with smartphones. We tend to use Wi-Fi while we are sometimes walking, right? So the thing is, as mobility is introduced in Wi-Fi, the performance degradation is expected. Especially, I talk about the kind of new features in the physical layer, like MIMO and wider bandwidth and so on. But the high-speed transmission means it's more vulnerable to mobility. And also, this is the one which I would like many talk about. I mentioned this frame aggregation, but the longer frame might have more errors, as I will show you in the next slide. So I don't know if you're familiar with Wi-Fi AMPDU, but it's called an Aggregate Mac Protocol Data Unit AMPDU. This is one of the core features of 11N and AC Mac Protocol. As shown in here, which shows along the time, this one represents a single AMPDU frame. So if you take a look at the inside, AMPDU is composed of a single file header, which could include preamble, and then a set of Mac subframes. So basically, without AMPDU, each subframe, which contains MPDU, should be transmitted individually. So, and especially in Wi-Fi, because it's based on CSMA CA Mac, between two consecutive Mac PDU transmissions, there should be backoff contention and so on, right? But by using AMPDU, multiple MPDUs are aggregated together, and then with a single preamble and physical header, they can be transmitted all together. So basically, the contention overhead, the backoff overhead, and all of them can be reduced. One thing is, because multiple frames are transmitted all together, basically the receiver, after receiving this, should acknowledge and negatively acknowledge each individual subframe reception. So that can be achieved by using block AGG. So block AGG, which is transmitted by the receiver, includes a bitmap where each bit represents NAC or AGG of each subframe. Okay? So again, the AMPDU was introduced in order to reduce the MAC overhead so that the throughput, overall throughput, can be enhanced significantly. So what happens is, especially with, say, for example, in old days with 11A, when 54 megabits per second transmission rate is used, the throughput at the MAC layer could be only around 30 megabps. So because of the overhead, the throughput was really low, but with AMPDU, depending on the situation. So what I mean by situation is depending on the frame size and traffic load and so on, the throughput can be around 80 to 90% of the transmission rate. So anyway, it's good because we can have this AMPDU and can transmit multiple subframes together and then reduce overhead and eventually can achieve high throughput, right? But the downside is, as I will show you later, this AMPDU is very vulnerable to mobile environment. Let's talk about this preamble and physical header part. So this one shows more detailed view of this part, physical layer, preamble, and header. I will not talk about the details, but basically this preamble is composed of legacy preamble and HT preamble and so on. It's kind of basically a set of known symbols which can be used by the receiver to detect incoming frame and then synchronize with the incoming frame so that the rest of the frame can be received. So what happens is, by receiving this preamble part, which includes training symbols, the receiver can learn channel state information, right? The thing is, Wi-Fi's OFDM symbol includes some pilot symbols which are embedded in each OFDM data symbol. These pilot symbols cannot be utilized to track the variation of the channel, but they are used to track the phase variation only. So anyway, because of that, what we can say is the CSI, which is channel state information, is learned only at the beginning of a frame reception, and that learned CSI will be used for the rest of frame reception. Okay? So what we can easily imagine is, if the channel changes over the course of frame reception, apparently we might have some errors, right? If the channel is very steady, it's no problem, right? But if the user moves around, or even if the user is just staying in one place, if the mobility mobility is observed in the environment because of your kind of friends moving and so on, then we can expect that OFDM symbols might have some errors for the latter part of this frame reception. Okay? So we experimentally observed and kind of confirmed that that's really the case. Okay? So in here, we used Microsoft Sora SDR platform for the receiver, and for the transmitter, we use Qualcomm Atheros chipset. And for 4 different mobility cases, that is 0 meter per second means no mobility, and up to 1 meter per second mobility, the x-axis represent OFDM symbol index. So 2000 means 2000 OFDM symbol in a long frame, okay? And the y-axis represent EVM, error vector magnitude, okay? And what we see in here is if the environment is very stationary, EVM stays flat, right? But for mobile environment, EVM keeps increasing, okay? So if we take a look at the signal constellation, at the front part of AMPDU, we see that this is 16 QAM constellation, right? But for the latter part of this AMPDU, we see this very blurred signal constellation, which means the signals can be anywhere. That means a lot of errors, right? So we confirm this again with commercial devices. So this is with, again, Qualcomm Atheros and also Intel 11N chipset. And in some environment where there's a single AP and when one mobile moves around, depending on the mobility, again, from 0 meter per second to 1 meter per second, and depending on the signal strength, 7 dBm and 15 dBm. And for both Atheros chipset and also Intel chipset, basically we measure throughput and also bit error rate for different subframe locations, okay? And if you take a look at the throughput, so let's take a look at just Atheros case. And with red color, that means 7 dBm signal strength. For no mobility, throughput is quite high, but as mobility increases, the throughput decreases like this. Well, actually, this kind of trend remains the same for high SNR or high signal strength too. So that means, irrespective of the signal strength, again, for the latter part of AMPDU, there might be a lot of errors. So it's not because of low SNR, but because of wrong channel information at the receiver. Okay? Again, that can be confirmed by looking at the bit error rate according to the subframe location. So at the beginning or the front part of frame, we have fairly low BER, but BER increases as the subframe location increases. Okay, so I think the message is really clear. Okay. Then what? We wanted to address and tackle this problem by solving 2 different possible approaches. One is called MoFA, which is Mobility Aware Frame Aggregation. And the second one is Tracer, which is Channel Aware Symbol Error Reduction. So basically this one, the idea is really simple. Basically, we observed that in mobility environment, the latter part of AMPDU experiences more error, right? So the simplest solution could be, what about just reducing the size of the frame so that we will not have high errors in the latter part, right? So with this approach, basically we adjust and adapt the frame length, okay? And that could be implemented by a simple modification of device driver, which is open source device driver. And also for the second part, well, actually this approach is kind of implementing frame length adaptation at the transmitter side. And this one involves receiving algorithm, baseband algorithm. So I'll talk about more details, but by iteratively estimating channel variation as part of the receiving process, basically this kind of incorrect CSI usage can be ameliorated. I'll show you more in detail. So this one is at the transmitter and this one is at the receiver. Actually, as I'll show you and claim later, both of them are kind of standard compliant and actually reasonably easy to implement. So I talk about this MoFA first. This one was presented in ACM Connect last year. Let's take a look at this figure. Basically, there is AP and a mobile, and AP transmit 5 millisecond long AMPDU. And after receiving this, the receiver will transmit blockhead, again with bin map, right? And this bin map will indicate which frame or subframe was correctly received and which were not. So in here, 1 represents successful frame reception or subframe reception, 0 means incorrect, unsuccessful frame reception. So again, in this figure, what it shows is, in the latter part, we have a lot of errors, right? So, by the way, this is a kind of illustration of our implementation algorithm, but we can do much better job. But this is really simple example or simple algorithm which we developed. So again, what we do is, by dividing the whole bin map into 2, half and half, we calculate subframe error rate for the front part and for the latter part. Okay? And if the difference, apparently, subframe error rate for the front part will be lower than the latter part, and by making the difference, we kind of compared this difference M with some threshold. And what we think is, what we basically kind of determine is, if this M, that's the gap between frontal and the latter part of parts, subframe error rate, if M is larger than some threshold, we conclude that, oh well, this environment is quite mobile, right? And then we better decrease or reduce the size of this AMPDU. So transmitter determines that it's better to take out the rest, okay? And then in here, the transmitter transmit shorter frame, which is earlier we had 5 millisecond long AMPDU, now transmitter transmit 3 millisecond long AMPDU. And apparently, this one will have mostly successful transmissions. Well, by doing so, sometimes the transmitter learns that, well, the channel state is much better than I thought, then probably I can increase the frame size. Okay? So basically, by trial and error approach, by using trial and error kind of approach, the transmitter can reduce or increase the frame size. Okay? And then in here, transmitter ends up kind of increasing the frame size by assuming that the channel state became better. Okay? I'll not talk about the details, but basically this one shows how our algorithm works. Basically, the transmitter determines whether the environment is more static or mobile by using kind of the criteria which I just explained. And depending on that, basically, the transmitter adjusts the frame size. Well, actually, I just said that frame size, but frame size can be represented by either number of bytes or time, but actually we use time. And also, we have another component which is called ARTS, adaptive usage of RTS, because what happens is the latter part of frame might have more errors, not because of this mobility, but because of hidden terminal too. So anyway, we have a kind of provision to take care of that too. But anyway, if I kind of talk about it more, basically our algorithm is kind of standard compliant. It does not require any change in the standard. And also, it could be implemented using commercial 11N devices with open source device driver. And also it requires the modification of the device driver only at the transmitter side. So now let's show you, let me show you some performance results. In here, there is only a single transmitter and single receiver. And here, the receiver stays and move half and half with regular pattern. It's like, move here, stay there, and then come back, stay here, like this, okay? And apparently, in this environment, there might be some mobility, and then stationary environment, mobility, stationary environment, and back and forth, okay? So, I show you two sets of graphs. Basically, in here, throughput, CDF, okay? And in here, along the time, what happens with throughput and the number of aggregated MPTUs or subframes. These green lines represent the performance with no aggregation, okay? And then this one shows the performance with optimal time bound for 1 meter per second. I think it was like 1 millisecond aggregation time bound. So with this, even if the mobile moves, irrespective of that, the number of aggregated frames is around 10, and the throughput performance is kind of relatively stable. And then CDF looks like this. But another curve now is with 11 and default setting. By the way, default time bound for 11N is 10 milliseconds. Okay, so with 10 milliseconds, almost 40 frames can be aggregated. But what we see in here is, as I said, the mobile moves, stay there, come back, stay there, and so on. So while mobile stays, the throughput is quite high, like this. But while the mobile moves, the throughput decreases a lot, and then decreases a lot here too. Okay? So what MoFA achieves is the best of these two. So basically, what we see in here is MoFA aggregate a lot of, like around 40 frames when it is stationary, and then MoFA aggregates small number of frames while the mobile is moving, and so on. And then by doing so, throughput can be quite high, irrespective of the mobility. And then if you take a look at CDF, the CDF curve is kind of, the most outer curve of all of these two, okay? Then, yeah, so we did some more measurement now in here with multiple nodes. So with 5 nodes, while out of 5, 3 are mobile and 2 are static. Basically, we made some measurements and we found that, again, MoFA achieved the best overall performance. What we see in here is, for these guys, the MoFA performance is quite similar to optimal time bound for 1 meter per second. However, for static devices, the throughput is much higher. Well, the thing is, it is kind of ironic that MoFA was developed for mobile environment, but the gain is observed for static devices. The reason is because mobile devices adjust the frame size depending on mobility, but static guys transmit the frames with the longest aggregation kind of bound, so that the gain is actually observed for static devices. But anyway, again, the point is overall network performance can be enhanced significantly by using this kind of simple frame length adaptation algorithm. Okay. The next one is tracer, which stands for channel-aware symbol error reduction. This one was presented in Infocom this year. For this one, the idea is again very simple. The idea is, if you take a look at this equation, the channel can be achieved by dividing the received signal symbol by actually transmitted signal, right? So, as I said, in original Wi-Fi, the channel is estimated at the beginning of frame reception by using known set of symbols. So, again, the idea is simple. if I know what was transmitted, and also by receiving the received signal, we can estimate the channel, right? So that's how Preamble and CSI estimation works. But we can use the same thing for the data transmission and reception too. How? By taking a look at this. Basically, this one shows the baseband operation of Wi-Fi, roughly. So this path represents the transmitting part, and this path represents the receiving part. So at the transmitting part, after scrambler, encoder, channel encoder, interleaver, and OFDM symbol mapper, and pilot insertion, and preamble insertion, and then transmitted. At the receiver, roughly speaking, the reverse operation is not made, but at the beginning, channel state information-based, per se, equalization is performed, and then pilot-based equalization, and demapper, and de-interleaver, and then eventually decoder, and this scrambler. But what we do in here is, by receiving a frame, we decode, and then eventually receiver retrieve the data symbol which was transmitted, and by assuming that this is the really transmitted data, actually receiver performs the process which should have been done at the transmitter. Okay, so by encoding, interleaving, mapping, and pilot insertion again, actually receiver regenerate transmitted symbol X. Okay, so if you take a look at this, this is actually true, but we can estimate transmitted signal, and then by dividing the received signal by by dividing received signal by estimated transmitted signal, we can estimate that this is the channel. And then by using exponential weighted moving average filter, actually the receiver can keep track of channel change without relying on preamble. So as I showed earlier, after kind of estimating channel at the beginning, keep estimating channel while receiving OFDM symbol. So this idea is really simple too. But the key in here is, can we believe that this is really transmitted signal? Well, actually the thing is, we can adjust this by using CRC, error detection code, which is embedded at the end of each subframe. Okay, so by using CRC error correct, I think it's incorrect to say error correction. So by using CRC assisted error detection, actually receiver can be assured that the frames or symbols, OFDM symbols, which were received up to that moment are correct, and by using those symbols, basically the channel can be kind of kept estimated during the reception of the data symbols. Actually, this algorithm requires the modification of the baseband processing at the receiver, and that cannot be apparently implemented using off-the-shelf commercial chipsets, right? So we used SDR, software-defined radio platform, which was provided by Microsoft. And then we implement this. Basically, Microsoft Sora, I don't know if you have experience with this, but I'm not really sure if it's the best SDR platform, but at least for us it was really nice in the sense that SDR, Microsoft Sora was implemented in such a manner that it can work with commercial devices. So we were able to receive off-the-shelf devices, Wi-Fi signal, and by decoding, and we were able to receive everything. Moreover, we implemented our tracer algorithm into this platform, and then we improved the baseband reception processing, as I said. Unfortunately, we could not do it in real time. We had to kind of process and run this algorithm in the offline because it requires some high computational complexity which could not be run in real time. Then this one shows the performance of tracer. Again, in here, x-axis represent subframe index, and y-axis represents subframe error rate. Earlier, with this MoFA work, we saw that subframe error rate is supposed to increase. So that's what we confirm with this Sora platform too. So for 0 meter per second up to 1 meter per second, as the mobility increases, the slope is higher. But anyway, the message is the latter part of subframe, the latter part of AMPDU experiences more error. But by using tracer, we see that the subframe error rate remains almost constant, irrespective of subframe index. And then the outcome is the throughput, right? So without tracer or baseline 11N, as the mobility increases, the throughput going down. But with tracer, it is affected a little bit, but not much. So basically, the throughput stays almost constant, irrespective of the mobility level. Okay, so I think that's it for the first part. So that is basically the message is mobility introduces more error for the latter part of aggregated frame. So we wanted to fix that problem by using two different approaches. One is at the transmitter part, and the other one is at the receiver part. Yes.
So could you do even better if you remove the requirement for? I mean, of course, violating the standard. Remove the requirement for CRC detection and rather redesign the pilots or
that's
redesign
possible. So actually, I will talk about that. One is there have been some proposals like inserting mid-ambles. So that could be one possibility. But with mid-amble, again, depending on the mobility, the error rate will increase and then go down again and kind of fluctuate like that. Another one is you talked about pilot, right? So apparently Wi-Fi has pilot. The number of pilots is too few to keep track of channel variation. Especially if you think about LTE. LTE use pilots, which is called reference signals, and they are kind of spread across, and then there are many reference signals so that the receiver can keep track of channel variation even with very high mobility. But in Wi-Fi, there are two facts. One is Wi-Fi, the channel bandwidth is similar to LTE. Roughly speaking, what I'm saying is Wi-Fi's channel bandwidth, default channel bandwidth is 20 megahertz. LTE's maximum channel bandwidth is 20 megahertz without carrier aggregation. So for the same bandwidth, the number of subcarriers of LTE is like tens of or more subcarriers. There are tens of more subcarriers. I mean, in the order of difference, magnitude difference. So LTE can have a lot more pilots, and then they can be used to keep track of channel variation. However, in Wi-Fi, for example, in 20 megahertz, there are around only 50 subcarriers, and there are like, I think, 4 or 6 pilots, So they are, the number of pilots is too few to keep track of channel variation. But another thing is, I don't know if you know that there is a standardization activity for 11AX.
That's what I'm asking.
Right. 11AX will have more subcarriers, and also 11AX is likely to have OFDMA. And then for that kind of features, we might have enough kind of pilots which can be used to keep track of channel variation even in mobile environment.
What is AX designed for?
11AX? 11AX is, the target is to improve Wi-Fi performance in highly dense environment. Yeah. But actually it talks about many different things too, like for more mobile environment and also for outdoor operation. And actually this is the unlicensed band at 2.4 gigahertz and probably in the future 5 gigahertz is so crowded, right? So how to solve the problem is their main concern. I'm not really sure if 11AX can solve this problem completely, but I'm sure that the standard people will continue to work on it so that the performance in highly dense environment can be improved eventually. Any other question?
Is there a point where you would need more pilots compared to your chaser approach? For example, if the signal to noise ratio becomes very low, would you have too many errors in your chaser estimation?
It's true too, but no. So the question is, if there are a lot of errors, which tracer will work, right? So my answer could be, in highly erroneous environment, Wi-Fi frame reception without tracer will not work very well anyway, right? So I believe tracer can help, but will not make things work worse. Okay.
I mean, arguably you want more if it's really fast environment. So Wi-Fi doesn't work.
Then now I move to the second part, which is energy efficient Wi-Fi operation. Earlier I said that Wi-Fi, the state-of-the-art Wi-Fi is at 11AC, which utilizes high auto modulation and a lot of antennas and also very large bandwidth. The key observation, as I will show you later, is well, actually, it's good that we have all these good features to achieve high transmission rate, but the cost is, one of the major costs is more energy consumption, and I'll show you the details. Another thing is Wi-Fi, of course it depends on the situation, might be a primary energy consumer in battery-powered mobile devices. I know that Wi-Fi is normally less energy consumer than LTE, but again, it depends on the situation too. If Wi-Fi involves a lot of errors and so on, Wi-Fi might end up consuming more errors than LTE too. The next one is Wi-Fi. I don't know if you're familiar with Wi-Fi, but Wi-Fi is based on CSMA-CA. So Wi-Fi device might be in one of the modes. One is transmission mode, receiving mode, or the rest is idle or channel sensing mode. Okay? So in order to transmit data, it should sense the channel first and then transmit, right? What's known is, in many situations, Wi-Fi devices spend a lot of time while just simply sensing the channel, and then ends up spending a lot of time for just channel sensing, which is called idling here, or it ends up consuming a lot of energy just by simply sensing the channel. To understand it better, let's take a look at this figure. So which one shows, again, transmitter part and receiving part, but just in the context of RF circuitry. It has a lot of components like power amp, filters, mixers, and DAC ADC, digital to analog converter, and analog to digital converter. So in order to talk about the channel sensing or idle mode, we have to focus on this part. Okay? So if we divide the power consumption into power components per each component, basically power for mixer, LNA, low noise amplifier, filter, amp, and so on, and finally for ADC. One key observation in here is power used for ADC is proportional to the bandwidth times number of antennas. Okay? So what we can imagine in here is, I said that with 11AC, wide bandwidth operation is defined also by using many antennas. So what we can easily imagine in here is, well, probably with 11AC, with a lot of antennas and wide bandwidth, probably the power can increase. Okay? So in order to confirm that, we made some measurement with some measurement tool. So this is PCI interface 11AC Wi-Fi, and then by using NI data acquisition tool, basically what we did was we took out some port and then added a very small register and then measured the current going through that register using this tool, and then eventually measured the power. So this graph shows the power consumption of this 11AC chip in idle mode, so during channel sensing. Okay, for 3 different cases because of antennas. So because 11AC chip can use up to 3 antennas, and also by measuring the power for all different bandwidth. So for 20 megahertz, 40, 80, and 160 was not available with this chipset, but based on the measurement of other bandwidth, we kind of made a model and then estimated for 160 megahertz channel 2. So we can make some key observations which kind of matches with what I expected already. So that is, as the number of antennas increases, the power increases, and as the bandwidth increases, power increases. Okay? So the power consumption heavily depends on the bandwidth and the number of antennas. Well, actually, we did measurement for idle and also receiving, transmitting, and so on, but I also show the power consumption for receiving mode too. The observation is almost the same, basically, as the number of antennas increases and also as the bandwidth increases, more power is consumed. But another thing what we observe in here is, depending on modulation coding scheme, the power consumption can vary too. So basically, for higher order modulation, so by using more complicated modulation and coding scheme, while at the cost of achieving higher transmission rate, more power is consumed, which is kind of obvious. So based on this observation, we also developed a very simple idea which kind of adjusts the bandwidth in order to achieve high energy efficiency. Well, this work was presented in IEEE SICON actually in June this year. Well, actually it's called WiZizz. I don't know if you know what ZIZZ means, but ZIZZ is like ZZ and when we kind of sleep. So basically what WiZizz means, basically in here, let Wi-Fi sleep when there is nothing much, okay? Well, it's a kind of, you might want to say what's the difference between this and slim mode operation of Wi-Fi. Slim mode is really slim mode. While in slim mode, basically Wi-Fi device does not even sense the channel. But while the Wi-Fi device is not in slim mode, basically it has to sense the channel. And then what WiZizz in here we say is, while the device sense the channel, let this device operate only using 20 megahertz, not the full bandwidth. Okay. So again, the idea is really simple. If you take a look at this, with baseline or 11AC operation, this is for data transmission reception. But while data reception and transmission is not occurring, even during channel sensing, the full bandwidth is used. And again, as I said, depending on the bandwidth, the power consumption, even for channel sensing, can be heavily different. And with WiZizz, basically, well, data transmission reception can be with 160 megahertz. But for idle channel sensing, what about using just 20 megahertz? So that the energy can be received, energy consumption can be reduced during this idle mode. Another thing is, I'll show you how this can be possible, but another thing is, let's assume that there's a single AP and 2 stations, okay? And AP sometimes transmit data to station 1 and sometimes to station 2. In here, initially AP transmit data to station 1. So station 1 receive data and transmit acknowledgement. Next, AP transmit data to station 2. at the beginning, station 1 is operating at 20 megahertz, and then AP1 learns that this data is not for itself, but for another guy. And then station 1 can stay with 20 megahertz, while the data using 160 megahertz is being received. So in here, by kind of ignoring the frame destined to other stations, extra power can be again saved. Okay?
What about the power to switch between the channels?
I'm sorry?
The power that the device used to switch between 20 megahertz channel and 160 megahertz channel.
I mean, overhead to switch the channel.
Yeah, different channels.
You mean the overhead to switch in terms of energy or time?
Energy.
Energy. Well, it's not that much. It's not that much. I'll talk about overhead for delay. But no, in terms of energy, so basically, so what you're saying is if the device has to switch between 20 and 160, there might be some extra overhead, right? But I think I cannot say by using some numbers, but based on our observation, it's not much. Okay?
It's usually just the output stage of the clock distribution. It's not. But
So, to achieve what I said, which is really simple idea, we propose two possible approaches. One is dynamic WiZizz, and the second one is pseudo-dynamic WiZizz. Instead of looking at this, let's take a look at this. I think if you're familiar with Wi-Fi, I assume that you all know what ITS, CTS is. So before transmitting data, transmitter transmit ITS control frame, which is short frame, and then receiver respond with CTS short control frame. And after a successful exchange of ITS and CTS, data and acknowledgement can follow. So with dynamic WiZizz, the assumption is, yeah, by the way, between RTS and CTS, CTS and data, there is very short time gap called SIFS, which is SIFS, which is only 16 microseconds long. So the assumption in here is, if channel switch, the bandwidth switch can occur in a very short time, which is shorter than SIFS, we can use this dynamic WiZizz. So what happens is, at the beginning, transmitter transmit ITS. Yeah, by the way, 11N and AC channel bonding was defined in such a manner that, where actually if this kind of frame is transmitted, they are duplicated in 20 megahertz range, kind of granularity. And also preambles are kind of duplicated too. So my point is, even if data is kind of occupying entire 160 megahertz, the initial part, preambles are kind of 20 megahertz bandwidth, and they are duplicated across this entire frame, frequency range. Okay. So anyway, the point is, transmitter transmit ITS, which is duplicated in kind of multiple frequency band, and then receiver, after receiving ITS, by taking a look at the signal inside the initial part of ITS, learns that, okay, now the transmitter will use this wideband transmission. Okay? So after receiving CTS using only 20 megahertz, because up to here the bandwidth of 20 megahertz is kind of used for the receiver, it switches to wideband. Okay? And then transmitter transmit this data by using the entire bandwidth. And then after receiving this data, the receiver switches back to narrowband, 20 megahertz, and then transmit acknowledgement. Apparently this is ideal in some sense, but as I said already, this one requires switch to 80 or 160 in a very short time. So in order to determine whether this is possible with today's devices, we did some measurement. Again, using Qualcomm Atheros 11AC chip. Basically, for depending on the number of antennas and also depending on the bandwidth change, we measured the power. So again, if you take a look at this, basically from 20 megahertz to 80 megahertz, we saw that the power increases like this in this much time. Okay, and then we conclude that this is the delay required for kind of bandwidth switch. And also, kind of related to your question, we see that kind of power increases, but there is no extra power consumption for the switch itself. Okay. So anyway, if you take a look at this, depending on the bandwidth adjustment or switch, and also depending on the number of antennas, the upward and downward delay occurs like this, okay? So, which could be like over 70 microseconds, can be as low as 22 microseconds. But the conclusion is, oops, I think the slide was modified. The conclusion is, all these values are longer than 16 microseconds. So the conclusion is, this, dynamic WiZizz is not implementable with today's devices. So we kind of conclude that, as I said, switching delay is larger than 6. So why don't we do it more in a slow manner instead of so dynamic? So we propose another one called pseudo-dynamic WiZizz. Well, the overall architecture is very similar. Instead of RTS CTS, we use a kind of short management frame called action frame. So by transmitting this, and receiver receive this, and then learn that transmitter will transmit with wideband. And here, the receiver switches to 80 megahertz, but with much longer time. Okay, but because transmitter and receiver exchange this delay in advance, basically transmitter will transmit after some time by using this 60 megahertz bandwidth. And the receiver transmit acknowledgement, again, is kind of duplicated. And then after some time, it will switch back to 20 megahertz. Okay? So this was very possible with today's commercial devices. And again, we implemented this with 11AC chip by changing the open source device driver. So I'll show you a couple of slides which shows the performance of the proposed WiZizz. The first one is with prototype and testbed experiment. Again, we implemented pseudo-dynamic WiZizz. This one shows the performance with a single node, single transmitter, single receiver. In here, multiple nodes. In here, as the source rate increases, power consumption is shown. The blue curve represents the performance of baseline. So by staying with 80 megahertz, and the red curve represents the performance of WiZizz. We observed that basically 25% energy saving is possible. And if you take a look at this one is with multiple node. And as the number of stations or receivers increases, the power consumption. In here, what we see is the performance gap between baseline and WiZizz increases as the number of stations increases. Well, the reason is, as I said, by using WiZizz, if an incoming frame which uses wide bandwidth is for somebody else, not for me, I can stay with 20 megahertz, right? So by doing so, as the number of stations increases, the performance gap between baseline and WiZizz can increase. And here, up to 55 energy saving was achieved. Well, the next one is we implemented dynamic WiZizz in NS3. Okay, so with NS3, we could do two things. One is, again, we could implement dynamic WiZizz. That is one thing, and the other one is we could test 160 megahertz operation. So commercial devices supported only 80 megahertz, while 11AC defines up to 160. So 160 megahertz operation was tested or simulated with 11AC. So if you compare this curve and this curve, they are for the basically same environment. But this one is with pseudo-dynamic, and this one is with dynamic. So what we see is, with pseudo-dynamic, 55% energy saving was achieved, with dynamic 57% energy saving was achieved. So pseudo-dynamic and dynamic are not too much different, but again, basically by using WiZizz, energy saving is possible. And if you go to 160 megahertz operation, again, this is not based on real measurement, but the power consumption with 160 megahertz was the kind of estimation based on our modeling. Of course, the model was made based on real measurement up to 80 megahertz. But anyway, with 160 megahertz, because 160 consumes a lot more power than 80, basically energy saving with 160 was up to 73%. So let me conclude my talk. In the first part, I talked about robust transmission of Wi-Fi in mobile environment, especially by looking at observing the fact that AMPDU, which was defined for throughput enhancement, involved or experienced more kind of errors at the latter part of long frame. We kind of wanted to or try to address or tackle that problem by either adjusting the frame length at the transmitter part or by implementing new receiving algorithm at the receiver. And in the second part, by observing that today's Wi-Fi consumes a lot more power than the other ones by using wider bandwidth and more number of antennas, larger number of antennas, especially in order to handle this wideband operation, we kind of proposed WiZizz, which allows the receiver or station stays with 20 megahertz, which is the lowest, narrowest bandwidth, and then only during transmission and reception it increases the bandwidth so that high transmission rate could be achieved. So I think that's it. So do you have any questions? Yes.